Hello children, welcome to Yamuna's physics classes. Today we have to discuss a topic, eddy current of the lesson electromagnetic induction section 6.8. So in this topic or in this video, what we are using or doing is, we should know why the term eddy, what's the meaning of eddy. Second thing, what is the reason for producing eddy current, and finally if it is good or if it is bad, is there some uses or some issues with eddy current. So these are the few things which we have to discuss, and for that we need to have a small experiment, just swinging simple pendulum, to and fro motion of a pendulum. That is very familiar thing. So what we know already is, if there is change in magnetic flux near a coil, there is induced current, and that is given by Faraday's second law, that we know. But here the question is, the same induced current and EMF can be generated if you are changing the magnetic flux linked with a conducting body or conducting rod or something like that. Anyway, conducting block or body, that's all. So what is eddy current? It's induced current in a conducting body due to change in magnetic flux. So we are just changing it. What we have studied is, there is induced current in a coil linked with magnetic flux. Whenever there is magnetic flux, change magnetic flux linked with a coil, there is induced EMF, that we know. But here, instead of that coil, we use the word conducting body. So it's come to the figure. You have a pivot. Over the pivot, you have a simple pendulum. Very simple pendulum. But attached to the simple pendulum, the string is a conducting body. So the string is attached to a conducting body. Just take a block, something like that. This is the block. The yellow shaded one is the block. This is the string of the suspension. This is the pivot where it is getting to and fro motion, just like a swing. But the importance is, if you don't have the pole pieces, what will happen? Just as a swing, it swings for a while, finally comes to rest due to a resistance. But here what is happening? Here the issue is, if the swing is happening in between the pole pieces of two magnets, what is happening is, the damping is much faster. Earlier it was slow damping, but here the oscillations die out, or the oscillations just comes to rest immediately. Means the damping process is fast. Clear? Or the time for damping to happen is low. Clear? Now what is the reason? And the reason is eddy current. Clear? Now let us explain. So what is happening? You know, when this is swinging between the magnets, what is happening? You know, it is shows magnetic field well into the south pole of the magnet. This is north pole. So the magnetic field lines are going well into the south of the magnet. So this is the direction of the magnetic field lines. As this is oscillating to and fro in between the pieces, you know, every time when it is coming and going out, what will happen? The number of lines passing through the block varies. Means flux varies. And specifically magnetic flux varies. Whenever there is change in magnetic flux, what will happen? Induced EMF. So this is the second law. What is the second law? The induced EMF is nothing but rate of change of magnetic flux with a minus sign. And here the minus sign is much more important. That is Lenz's law, you know. So we will go to the next session. What's the next session? Why the minus is so significant here? It is significant, okay, but here it is doubly significant. Why? The reason is, I said it is fast damping, or the time for damping has come down. Why? And the answer is Lenz's law. The answer is Lenz's law. So what's the first thing? Whenever there is change in magnetic field flux as it is oscillating to and fro motion, number of lines varies, flux varies. When magnetic flux varies, EMF is induced. Clear? Inside this block. Now the question, why it is suddenly damping? Answer is Lenz's law. What is Lenz's law? Lenz's law says that whatever is the cause, oppose the cause. What is the cause? d phi by dt. What is the result? Induced EMF. And the induced EMF should be in such a manner that it should oppose the cause. Meaning, example, suppose this is coming out of the field. So what happens? Lenz's law comes to play. So once it is going out, Lenz's law meaning induced EMF should be created inside this, or induced current, E by R gives the induced current, should be in such a manner that it has to return back. Means if you have to pull it back, what should happen? This is north pole. So if this is the oscillating metal block, this is the north pole I have here. So this side of the block should be obviously south. By it has to put it back. So the metal block is moving out of the magnetic field, but I am pulling it in the reverse manner towards the north pole. So this side means this side of the block has to be south, the other side should be obviously north. And moreover, you know, inside this, I told you it is south, meaning this I have drawn as S, but you see it is clockwise. So here the current will be in clockwise direction. Inside the metal block, over this side, that is side which is close to the north pole, it will be south, and close to the south pole, this side will be north. So that block which is going out is brought back inside. Now what about the reverse case? If it is entering the magnetic field, what will happen? Again opposition. So you have to go again out. So what will happen? This side becomes north. Means this is already north. So when it's getting in, this side behaves as a north pole. Means the magnetic, the north N is written in which manner? Anti-clockwise direction. So the induced current here will be north, showing anti-clockwise. Induced current here, it will be showing south, clockwise. Means the induced current reverses the direction once it is coming in and once it is going out. Why? To reverse the effect. Once it is going out, pull it back. Once it is coming in, push it back. So that process is Lenz's law. Now, why the name eddy current? The question is, this kind of current which is well inside the block, if it is south or north, clockwise or anti-clockwise, it results in the eddy current is just by the term induced current. Basically it is induced current. But why the name eddy current? Because you know it is in magnetic field. So inside this there is magnetic force. So if there is magnetic force, what happens? There is free electrons inside the metal. What will happen for the free electrons? They are affected by magnetic force and they results in the movement, and it moves in such a manner like whirlpool. You have heard the term whirlpool inside the water. It resembles a whirlpool. Hence the term eddy. Eddy, the word meaning is like a whirlpool. So that particular whirlpool which is formed inside this metal block or conducting block is known as eddy current. So eddy current is nothing but induced current. Just because of the nature is resembling a whirlpool, it is known as eddy. Clear? So 2 questions answered. Why there is sudden damping and why there is the name eddy current. Clear? Okay. Now look at it. Due to eddy current, 2 things are happening. I told you what is one thing. What is one thing? Sudden damping. What is the second thing? Eddy current forms in the manner of whirlpool, and also this current inside, you studied magnetic dipole moment is I into A. I means the induced current, A means the area. So that is magnetic dipole moment inside this metal block. So due to that, it is fast damping. So due to that, a resistance increases and heating effect increases, meaning it starts getting heated. So two unnecessary things are happening. Number one, fast damping. Two, heat generation. So how to reduce these two things? Number one, you can use slots. This whole block can be cut in this manner, and in between the pieces you can remove so that it resembles like a comb fashion. You can have a strip with small slots inside. So you can reduce the size of IA. IA can be a big loop. That big loop you can make to a small loop so that the effect of the eddy current is already present there, but the damping, fast damping can be slowed down. So thus you can reduce eddy current. And lamination. Why laminating? Instead of taking a metal block as a whole, you can slice it into different plates, then put together. Each plate should be covered with a lamination like plastic or something, so that the heat generated from one should not go to the other and should not multiply. So when you are splitting and placing with lamination in between, what will happen? Heat conduction will be slowed down. So here the damping will be slowed down. Here the heat formation will be slowed down. So this is how you minimize eddy currents. But is there any use? Definitely. The damping of the fast damping or sudden damping results in magnetic braking in bullet trains. What is bullet trains? Fast moving trains. So there you have pair of magnets in between the track and the wheel. So no wear and tear, nothing, no mechanical energy loss. So it's smooth landing just because of immediate magnetic braking. So immediate damping is used in bullet trains. Another one, electromagnetic damping. We have deadbeat galvanometers like that in the lab where you need sudden damping. So there also you can use electromagnetic damping, can be used in deadbeat galvanometers. And induction furnace. What's the use of induction furnace? I told you the heat is getting generated. So if you are placing a powerful magnet, swinging in such a manner that it gets melted. The metal gets melted. So induction furnace. And moreover, at our home we have power meters. Current supply is read by power meters. In that electric power meters also this application is made use of. So we discussed three things. What are the three things? Why the term eddy? What is eddy current? Is there any use? Is there any measures to slow down or to reduce eddy currents? Hope it is clear. So you can have a screenshot of the notes and you can take down. Thank you for listening. Thank you.